right, hey guys, thanks all for coming. It's good to see some familiar faces as well. Yeah, so we're going to talk about general circuit safety and go over like the landscape a bit, what vulnerabilities have existed. We'll touch on one to do with proving systems. It was Frozen Heart, and then we're going to talk a little bit about like nullifier duplication issues, underconstrained circuits, and try and like visualize what exactly those vulnerabilities mean, because I know that whenever I was first researching this stuff, I kind of it took me a while to kind of understand what under constraint actually meant behind the scenes, and not just it being an issue, like how to prevent it, what it actually means. So yeah, I'm going to dive in. So yeah, just as I said, going to briefly go over the programming model as proving system vulnerabilities, common bugs, Noir. I'm going to talk about Noir and Aztec 3, which is our next generation rollup that we're building, which will have Noir as the smart contract language, so you can write private circuits, private smart contracts that will be powered by Noir. And then we're going to talk about a feature in Noir. Max is going to talk about this, which is unconstrained functions, which is something that we think will be a bit of a foot gun for people writing circuits, and we just kind of want to talk about it so you guys know what to look for if you ever have to audit Noir. So this goes without saying, ZK is a bit of a buzzword at the minute. Everyone's doing it, I guess. It's useful for either information hiding, so the zero knowledge part, or it's useful for succinctness, and you'll see a lot of rollups are built around this. But we at Aztec, we use both. So we have a rollup for high throughput, but also you can have private transactions on that. So the model is a little bit different to writing traditional programs, where you write a program with the intention of getting some output at the end. Within ZK programming, what you're thinking about is how do you constrain that this is the correct output. So you'll have some kind of language or a DSL that will create constraints. You will then have some way of generating witness values that will conform to those constraints. You will give those to a prover that will create a proof, and then you'll have a verifier that will, in the context of snarks, will have some kind of verification key that will be able to check a proof for those constraints. And it's all very succinct and very nice, and a lot of magic goes on behind the scenes. So there's a couple of vulnerability classes whenever in the world of ZK. So we have actual proving system vulnerabilities. I'm going to go over one that was found by Trilobits last year that they've dubbed Frozen Heart, which was a problem in the papers for Plonk and bulletproofs. And then secondly, we're going to talk about common vulnerabilities when creating circuits, and hopefully we'll have some examples and some way to visualize them as well. So whenever you're writing circuits, it's very important that you pick a proving scheme that you trust. It's a huge dependency, because if there's a flaw in your proving scheme or the implementation of your proving scheme, you're fucked. There's no other way around it. So in this case, we'll look at Frozen Heart, which was an implementation issue of Plonk that was caused by a lack of guidance in how something called a Fiat-Shamir heuristic was implemented. So in the Plonk paper, it says it itself describes an interactive protocol, and it says that you can make it non-interactive with the Fiat-Shamir heuristic, but it doesn't really say anything about how to implement that. And what the Fiat-Shamir heuristic does is convert an interactive proof into a non-interactive one. So in this slide, we're going to kind of look at what the Fiat-Shamir heuristic is. So if you imagine, there's an example that's used a lot when trying to explain zero knowledge proofs, and it's, say I'm a colorblind person and I have a green ball and a red ball in each of my hands, and I put them behind my back and swap them around and then present them to you, and you can tell me if I've swapped my hands. And I do that a certain amount of times until I'm sure that you know the colors of the balls, and I don't. You can kind of think the same way for how an interactive scheme works, where you give me a commitment to some value, I present you a challenge, and then you prove to me that you can evaluate at that challenge value. So on the right, we kind of have a little diagram which is showing that you've got multiple hops between prove and verifier until the verifier is convinced. At the heart of the Fiat-Shamir heuristic, you basically take the proof, which is known as a transcript, and you create challenges by hashing certain parts of the proof. So on the right, you see that challenge 1 is the hash of 3 public inputs. I don't know if you guys can see my mouse, but I'm kind of waving over them here. Challenge 2 is a hash of challenge 1 with some other random points from the transcript. And then challenge 3 is a hash of the challenge beforehand at some other, with some other points in the transcript. So what you can do, instead of having multiple hops like we have here, both the prover and verifier deterministically know how they can generate the challenges. So the prover can just send over the transcript with evaluations at each of the challenges, and then the verifier in its verification phase will have points that generate these challenges again and evaluate certain points against them. The problem is, in the Plonk paper, there was nothing directly said over how you generate these challenges. So in this example, before, I've included a hash of the public inputs, a hash of certain evaluations, and a hash of a different set of evaluations. Let's imagine that I leave the public inputs out of this hash. It creates a problem where the randomness is not determined from the public inputs anymore. And they're not, even though they're in the transcript, there's nothing, they're not checked against. So if your public inputs can change, you can use the same proof with changed public inputs and get the proof to verify if your proving system doesn't implement Fiat-Shamir correctly. So the problem was here that you could technically forge proofs if you didn't hash the entire transcript. And I think it was Gnark didn't do it properly. Some other implementations didn't do it properly. But the idea was that it was kind of an implementation detail that meant you could forge proofs, but in practice it would be really difficult to do because you would have to do a lot of hashing and make everything line up. So yeah, I just wanted to paint an example of that proving systems aren't bulletproof. They're not, you can't always rely on them to be 100% correct. Cryptographers, although superhuman, do make mistakes. So yeah. Okay, common circuit vulnerabilities. We have under-constrained circuits. This is when your witness values that you inject into a circuit aren't necessarily constrained to be a certain value. And this is something I'm going to try and illustrate in a little bit more detail at what this actually looks like under the hood and how under-constrained circuits come to be. There's problems where if you don't necessarily constrain bit lengths inside your circuit, you can have runaway values that will construct valid proofs. And then there are also certain double spend issues that are really common. And I'll go over a bug that was in Aztec related to this as well. So these are under-constrained circuits are a problem, and they're out there in the wild. There was actually one of the original implementations of Tornado Cache that was vulnerable to one, and they had to white hack themselves to get rid of it. So so what is an under-constrained circuit? I've kind of talked about it before. It's a circuit that does not have the correct rules to fulfill its intended purpose. So the developer may have intended it to do one thing, but in practice it doesn't actually do what's intended. So yeah, I'm going to take a quick detour into Plonkland and kind of try and illustrate what an under-constrained circuit looks like under the hood. And then I will show you what the fix was for the Tornado Cache issue. So let's say we have a hash function that takes a hash of x and it will hash to y. So the preimage is x and the output is y. in general, in the Plonk construction, you'll have something that looks like this. So we have a public input, which is the value x. We have a output to our circuit, which is y, which is also going to be a public input. We then have a set of gates here, which will be a hash function. So we have some kind of plus operation or multiplication operation on the two values, in the values in columns A and B, and they will give us some value C. So this is kind of what Plonkish arithmetization looks like under the hood, if we're using a 3-wire setup. And the problem is that let's say we have an input X and an input Y and some hash trace here that ends up with X and ends with Y. So our preimage and our hash value. If I don't specifically constrain the input that I've given Y to be the output of my hash function, then my circuit is under constrained, and I actually haven't. You can technically put any output in Y and still have a valid proof. It doesn't actually matter what your hash output ended up being in the circuit. So Plonk's way around this is by things called copy constraints. So let's say I have, so in box 2C, I have the value Y. I need to constrain that equals the value in our nth row here, NC. And this is kind of a subset of the copy constraints for the current circuit for some kind of hash circuit. So we have that like 1C, this X will have to equal this X. We have this Y will have to equal this Y. We have this some value T has to equal this some value 2. This some value n minus 1 has to equal this one, and so on and so forth. You just have to make sure that you provide those. And this was the bug that was inside circumlib that caused the middle cache. We have an assignment, but this assignment wasn't constrained. So as you can see here, we have Y is assigned at this point, but unless we have this copy constraint which sets it to this output, then we can in fact create proofs that we can basically put in any hash output and it just won't matter. So yeah, it's a really small like semantic fix in Circom. It's honestly like you could consider it a bug that it lets you do assignments without constraints. But if you want to optimize, it's something you require. You can kind of think of it as like writing footguns in Huff or something like that. Like just because you can have efficiency doesn't mean it's a good thing. So yeah, this is something that Noir fixes. You can't do something like this. You can't have a public input that's unconstrained. You can't do an assignment to some important value and not constrain it. Like Noir will do that all for you. So if you're a new dev, I would definitely recommend picking up Noir before you experiment with Circom. So yeah, under constrained circuits are definitely a big problem in Circom land. And the reason is being, as I said, that Circom is a pretty low-level language. But it's getting harder to write unconstrained circuits because a lot of good static analysis tools are being invented. So just the way like reentrancy was a massive problem in the early Solidity days, well, kind of still is a big problem if I'm honest. There's a lot of static analysis tools like Slither that can kind of find those bugs for you, or like even overflows. Yeah, there are these tools. Veridice of Picus, which is a static analyzer for Circom, and Trilobits have also got one called Circumspect, which are super useful and will catch most of these bugs. Or you could just use Noir and just not worry about it in the first place. So yeah, there's another set of vulnerabilities that you'll find in general circuit land, and they're vulnerabilities that you'll find in any programming language. So we have overflow and underflow, and then signature malleability. So I'm going to talk about overflow and underflow first. Everything in a circuit will be mod some prime number. So let's say for most things in the Ethereum ecosystem will be on the BN254 curve, or at least some curve cycle of it. And they will have a 254-bit prime that everything is mod by. So if you have any values that are larger than that, you will need to constrain them. You will need to do range checks. I think the TLDR for this one is just do range constraints everywhere, and you won't have anything to worry about. Next, we've got like signature malleability. This is very similar to how if you're doing like an airdrop claim in Solidity, you don't use the signature as your, well, you could say nullifier, that a signature is that something has been claimed, because you can just create another valid signature for the same address that's different. The same exists in circuits. So if you imagine the private state model for most zero knowledge programs will be that there's some kind of data tree and there's a nullifier tree. So if I want to, in Ethereum, if I want to update state, I just update a certain storage slot. I can't do that in a private context because people will know what slot I've touched. They'll know whose data I'm touching. They will know if, let's say, they will know what notes I've spent, essentially. So the way we get around that in ZK world is by having a two-tree model, and this is what Tornado Cache has, and this is what Aztec Connect has, and Zcash as well. So if I want to add some piece of state, I add a note in my data tree. If I want to spend a value, I add a matching nullifier to the nullifier tree. But there are a class of bugs that will allow me to add a second note to my nullifier tree. And that will basically mean that in my circuit, I've tried to check if a nullifier already exists for the value, and then I've failed to catch that, or there's been some kind of malleability for my nullifier, and I've been able to insert it twice, and that's not good. So a classic example for ECDSA is their signatures. So just as I said, every signature will have an R and S value, but also if you take your S value to be minus the prime field, so you take the prime field and then minus the S value, it will be another valid signature for the exact same public key message combination. So even here we have R and S and RP minus S are two nullifiers that will work if we use a signature as our nullifier, which means there was a many-to-one relationship between a piece of data and its nullifier. So watch out for this. In general, if someone's using a signature to construct some kind of nullifier scheme, it's probably badly designed in the first place. This was a real-world vulnerability, and it was in 0x Part Stealth Drop. They've written an amazing write-up about it in their GitHub README. Definitely worth checking out if you want to understand this a little bit better. And then another type of nullifier or like nullifier reuse vulnerability is a mismatching bit length one. So if you don't constrain the number of bits a value has in your circuit, you can potentially run into nullifier duplication issues. So this was actually a production vulnerability in Aztec Connect that not many people know about. It was not exploitable because we have a centralized sequencer, or we had a centralized sequencer, RIP, and nobody else could submit proofs. But if Aztec Connect was decentralized, this would have been a bad issue. So each nullifier had an index in a tree that was 32 bits. This 32 bits was not constrained to be 32 bits. So it did a check on a 32-bit value, but it didn't check if there were more than 32 bits in the value that was being checked, which meant that if you added, in the example, you can kind of see in the image below, if I have 32 bits and another 32 bits, and I just added some arbitrary value to the end, the first check would pass because it checked 32 bits equaled some kind of pre-image, and then it wouldn't check after, and you could insert multiple nullifiers in the tree, which is not great. So yeah, I'm gonna now talk about the current language landscape. We have Circom, which is a low-level, very highly customizable language. You can have unconstrained parts you want. You don't have to constrain. You can constrain things you want to. If you look at like the pyramid of language construction, Noir at the top is the least complex, easiest to work with. You can probably get a circuit up and running in 5 minutes, which we might try and do at the end of this presentation if we have time. We have Circom, which is a bit of a pain. And then we have hand wiring circuits, which is max pain. It's pretty annoying, and really you need to be a cryptographer at that point. So yeah, in Aztec we actually write most of our circuits in C++. which is pretty painful to say the least. And this is what it looks like. In Circom, looks like this. In my opinion, it's somehow worse than writing them in C++. I actually wildly prefer this to this. And then we have Noir, which Max is going to now talk about, and is really easy to get started with. So, Max, do you want to take the stage?
Yeah, should I switch to the share?
Yeah.
Well, Sean gave a pretty good intro, but the goal here is to enable you to actually write ZK like a normal you would expect in normal programming languages, and not in this only way that only really cryptographers can understand. So, as we've gone through, a lot of the current needs or the existing languages require an advanced cryptography background, and you're manually writing a lot of constraints, which can lead to a lot more bugs. So yeah, our solution to that is Noir. A little preliminary warning here: Noir is still heavy in development, but yeah, we're constantly finding bugs and fixing them, and it's also why we're speaking to you now. Sorry, I was just reading the chat real quick. So this is kind of a joke here. We're saying, spot the difference between these two functions, but the joke is that there is no difference. The left side's Noir and the right side's Rust, but they look the same. The goal here is just to, get people into working in an environment where they are actually, it's like they're writing Python or writing Rust. So we have the classic primitive types you'd expect, but the one thing that's different here is we have a field. That's because everything is based upon the base field of the proving system that Noir compiles into. So here, that if we're compiling with the Aztec backend with Berettenberg, that's the base field of the BN254 curve. We have arrays, which you can see in this example here, tuples, and we also have struct types as well. And you can impl on these struct types and add methods to them. Also have functions, and we let you break these functions up into modules and import them as libraries. And we also have for loops and if statements, and logical and bitwise operators. If our bitwise operator kind of acts as our logical operator, as you can see there, we just are doing an and on the bools. And we have, of course, many more other features. Some of the more exciting features that we added recently are generics and first-class functions. We're going to be hopefully have vectors soon, and then there's some other features that we're going to dive into more that relate more tightly to Noir contracts that we're going to get into. The main, I just want to recap though of what one of Noir's main selling points is though, is that we don't just compile down to a proving system on its own. We compile down to an IR, which we then translate to a given proving system. And our IR we call the abstract circuit intermediate representation, or ACER. This IR can then be compiled down to any MP complete language. This could be like R1CS or Planckish languages. This means that Noir is fully backend agnostic, and right now we're fully integrated with TurboPlanck, but we're extendable to the proving systems you see listed there. And recently, Lambda class actually did a Planck and Gros16 implementation with Noir, integrating it into us. So this is one of the main things that Noir wants to be extensible to the community, even though we're becoming a contract language with Aztec as well. And part of being extensible in this way is our IR enables proving system optimizations, which essentially means custom gates. And we expose multiple efficient functions from like Aztec's Berettenberg in Noir currently. We're trying to achieve this kind of pyramid here. We want to be a secure language, but we still want to be simple enough while remaining performant. So this is definitely challenging, but we think it's possible. So something we want to mention that we also a recent feature that's really makes testing just so much better than it would be, because otherwise you're writing all your tests in TypeScript. This is just we enable you to test directly in Noir.
Yeah, this is a massive UX improvement over writing in Circom or anything else, where you have to compile everything in some kind of TypeScript setting and then construct proofs with some kind of TypeScript library and then send them over. You can just run Nargo test and it will just do everything for you. It's great.
So today, if you want to have a ZK app, you're going to deploy your contract or something onto Ethereum, and then you're going to be verifying that contract using some sort of validity verifier. But this kind of leads to its own challenges. Mainly meaning how do you deal with and how do you interact with private state, and how are we actually going to store that on the EVM in one secure way, and then also is it possible to share it at all? So currently we have multiple different ZK dApps. Right here you see a few popular ones: Dark Forest, Tornado Cache. That's BattleZips, who was a Aztec grantee. They built implementations of battleships in Circom, Noir, and Halo 2. And then NounsDAO, who recently just commissioned a private voting research sprint that Aztec is taking part in. So each of these projects, though, manages their own private state. They all have a Merkle tree for which they're checking participants and using and notes in that tree for being able to do private transactions. So what we're trying to do with Aztec is bring that into a shared execution and storage environment. And that'll be in Noir contracts, where you're not going to have to actually manage that tree. Oh, you can, yeah, go to the next one. The Noir, you're not going to have to manage the tree as a Noir circuit developer, because that'll be all baked into the execution environment itself. And that's what Aztec 3 is going to enable. And there'll soon be some more Noir things to see with that. So Aztec 3, we're a ZK rollup, as Aztec Connect was, that though will actually enable fully programmable private and public state. So Noir is going to have private and public smart contracts, meaning you're going to have private functions that will be executed on the client device and public functions by the public execution environment. And Aztec 3 will be that environment for Noir. So one of the critical changes that is being brought to Noir will be that we're going to have to actually fetch information from this private state somehow. And we're going to use this concept that we enable that is used already in Noir called Nondeterminism. We have in our intermediate representation I brought up earlier, we have a few opcodes, but one of them is the directive, and this is how we bring in this idea of nondeterminism. I'm going to briefly go through how we use it in Noir now and how it's going to apply to Aztec 3, future Noir contracts, and where you can possibly have some vulnerabilities. So directives don't apply any actual constraints down. They just inject information into the witness. This is the prover is doing it on their own. And right now, directives are restricted to our VM, as they're just an opcode in the VM. And the constraints for this oracle are being written somewhere else during Noir compilation. So the key thing, though, to take note of is that Noir just wants to prove that some computation was done correctly. It's not enough to simply give the result of the program. We need to actually prove that something was done. So even though that non-determinism can let us do some really cool things, like inject information, but it needs to be handled correctly. So I'm going to just go through a brief example. Let's say I want to do like some simple operation like decompose our native field type into a byte array or a bit array. The straightforward approach is just to convert it into some sort of U32 and then perform some bit operations to transform it into an array. That's what I did in that very rough pseudocode on the right there. The problem with this approach, though, is that it's, one, expensive to do bit operations inside of a ZK snark circuit. It's also incomplete. Right now with Noir, we have a limit on our sizes for bit arrays for bit like unsigned types. So we can't even decompose a field of like large size. So what we can do instead is lay down some arithmetic constraints in the Seer that we have a byte array that follows this equation here. However, there's a problem with just doing it this way as well, because for the verifier, it's this statement holds, they can fulfill this equation. But for the prover, they can't implicitly determine what the values of the array could be. So this is actually what the idea of nondeterminism is. The prover does not know what values, could the array 0 just be 1000 and the rest of the array is just 0? Or the array in this, following this arithmetic constraint is actually the valid byte array. So the prover has to inject the correct values into the arithmetic constraint above and then constrain them. The directive just takes the values and injects them into the witness. While during Noir compilation and Acer generation, that's when we lay down the arithmetic constraints separately. So this concept can be brought to unconstrained functions. And it's essentially extending this directive. We're going to make it more generic and enable full nondeterminism in Noir, where users can run unconstrained code. These functions will execute outside the circuit, similar to our directive. They're just now going to be specified by the user rather than our VM. And an important part, and this is kind of the footgun we think is going to be mainly existing in Noir contracts, is users are going to have to make sure to constrain the outputs of any unconstrained functions they're using in the Noir program as well. And that's when you can start finding bugs similar to what Sean presented in Tornado Cache. So here's an example of this syntax isn't entirely decided, but of what might be happening in Aztec. You have some UTXO set, and you need to determine, what is the actual balance of the person trying to transfer some funds. You're going to have to find all the funds according to that user, but then you're going to have to make sure to constrain it in the circuit as well. Because when you're running this code, the information you're fetching has to come from the Aztec 3 client. So you're doing some sort of database query for some note information, and you potentially, if you don't constrain it in the circuit itself, could lead to your processing falsified information. So, and then you'd see an exploit. That is mainly it, I think. We have, if we have some time for questions, we can go through that, or we can do a little demo where we show us just setting up a Noir circuit and proving and verifying.
All right, yeah, I'll give that a go. All right, so let me see. Let's see if this works. So I'm going to do Nargo new demo. And hold on, is the sizing good for all this? I'll make it a little bit bigger. Okay, this will do. So Nargo new demo, that'll create a new repo called demo that will include a source file, which is our .noir, and then a TOML file, which is kind of our project configuration. So we can import dependencies in from here. We then have a simple circuit, which is constrain that X and Y are different. So if I were just to write a little test about this, I want to do okay, that's not correct, but close enough, autopilot. So I just write a test, and then I would say, let's say X equals 1, let's say Y equals 2, and I want to call my main function and say X and Y as 1 and 2. So what should happen here is if I run Nargo test, we have a passing test. If I want to change this to be 3, or change this back to be 2, I should get a failure, and it'll tell us that this constraint doesn't hold for the values we've given. So I managed to get a test up and running within 2 minutes, even with technical difficulties, which this would have taken a lot longer to do in something like Circom or anything else. If I want to compile this and create what we call a Seer that you can then generate a proof from, I literally just do Nargo compile and give it some name, and then that generates a target folder with our proving key, which is everything a prover needs to create a proof, a verification key, which is everything a verifier needs to create a proof. If I then want to create some kind of Solidity verifier for this, I can just say Nargo contract. And now I have a Solidity contract, which I can send proof data to. I don't know if I'll have time to whip out a Foundry repo and get proofs working. But yeah, it's all very simple. Everything's built into this package manager called Nargo, which you can download pretty easily by getting Noir up and then running it. And that'll download the latest binaries. I'm not going to do that in case they're broken. But yeah, you can see if I want to create a proof, I can just go Nargo prove p. Oh wait, I need to create a prover.toml first. We do that.
You can just run Nargo check.
Will I create one?
If you run Nargo check, it'll auto-generate 2 files.
Ah, there we go. And then I can set my values to be 1 or 2, 1 and 2, and then run Nargo prove p. And now I have a folder with a proof, and this is a proof for this toml file. And then if I want to verify that with that proof, it'll basically run.
Yeah, no output means it's all good.
Yeah. So that's kind of everything in Nargo, kind of gone over really quickly. How you can write a function really easily, test it really easily, and yeah, it's pretty good. So it will be, it'll stay general purpose. So if I have just a main.noir function here, everything will be, it'll stay the same. If I add in the contract syntax, which doesn't actually exist yet, but say I do this and I change the name to be like not equal. Now it becomes a smart contract language. But at the same time, but yeah, so if I just remove this super contract, I think this is what it'll look like, then it will behave as it has. And there's a lot of work being done to have alternative proving systems. As was said, Lambda class have got Gnark wired up, which has a Graph16 and standard Plonk in it, which is fantastic. So you can use more than Turbo Plonk if you want to. And Ultra Plonk is just around the corner, which will have lookup table support built in. So a lot of the standard library functions will be really, really fast, which is, yeah, it's developing a lot. And I think somebody made a Halo 2, like a proof of concept Halo 2 implementation, like backend that uses succinct's KCG Halo 2, which is really good. Oh, wow. Big question. Max, do you want to start talking about the challenges of Noir, like developing the language in general?
Yeah. We actually just had a big offsite where we had a lot of challenges that we ran into, but it was I'd say with Noir itself, it's just making sure dealing within the ZK environment is different than the normal paradigm we're used to with normal programming. Like I said, your reasoning about proving, it's not enough to just spit out some information. You're laying down constraints. So like in those directives, I like highlighted like this isn't doing any sort of laying down of constraints. It's happening somewhere else. So that's definitely challenging. And just now starting to reason about actually interacting with private state in a safe manner is definitely hard. And it's kind of a battle. It's like, how much do you leave to the developer? There's definitely going to be some that's the developer is going to have to do. And that's probably where auditing Noir contracts is going to become a big part of Aztec 3.
And then challenges we've had for the private state thing. If you imagine, if you want to have a generalized smart contract protocol that's private, how how do you do private state in the first place is that you actually need the user to execute the functions on their device. As soon as you, let's say the traditional model that you have for like some kind of ZK EVM or even just the EVM in general is you construct a piece of call data, you then send it to a node, and the node will execute that for you. If you try to do anything like that with private state, as soon as you send it to someone else, you've leaked the information that you're trying to hide, or you've revealed to somebody what tree indexes you're accessing and what state is yours. You're revealing information about, or even like, it's everything in the current blockchain model just leaks information. So what we've had to build is a way for you to compose like multiple circuit calls into one. So if you imagine you have one contract which is like do something, and then you have like, let's say it has a function A. Oh, Noir syntax, it'll be funny. And it returns something. Let's say it returns a unit 64, and maybe it gets some value, or I don't know. And then you have like contract. Maybe I should change the names of these. So I'll do something. Contract A, contract B, fun, do another thing. And let's say that this calls contract A. If these two functions have two different verification keys, how do you call function B from function A? Do you stitch them together? How do you call function A from function B? Do you have to stitch them together? Do you create an entirely new circuit that just concatenates A and B? Like, what do you do? And what we've created is something called a big massive circuit called a kernel circuit that allows you to stitch multiple function calls together based on a series of verification keys. So what happens is a user will construct a call to multiple contracts. They will then run on their device something called the kernel circuit that will then create all the state updates that need to be created, and then it will send all of it as one black box to the node. So if you imagine you basically pre-execute a function on Ethereum, and then you have to then execute that on a user's device, but then also construct a proof on a user's device. So you can imagine there's a couple of like blockers there. You need a proving system that's fast enough to be run on user devices and not take up an outrageous amount of RAM. Like a ZK EVM, Scroll ZK EVM, at some point their prototype used 675 gigabytes of RAM to run. If you're trying to create a private VM, you just can't have that. So there's been a lot of engineering problems around creating a proving system fast enough to work on mobile devices and be able to do complex call stitching. And we've got that. We've got a new proving system coming out called Honk, which was actually developed in tandem with Hyperplonk and uses a lot of the same ideas. And then we have this, as I said, we have something called a kernel circuit, which allows you to construct all these calls together. And then there's a lot of problems around state growth and how do we manage that. And yeah, a lot of challenges, definitely. So yeah, I hope that answers the question somewhat and kind of gives you an idea of like what we're building as well and where potential problems will be that you guys, auditors, can tap into. Max,
Yeah.
you want to take it?
Yeah, I can take this. So the big thing is this contract feature. We're trying to get Noir syntax for Aztec 3. On the language itself, we're constantly working on improving right now been making a big switch from TurboPlunk to UltraPlunk that had some difficulties we didn't foresee, and our tooling team is going to be working on really making Nargo an amazing package management tool. And yeah, we are right now a bit heads down on Aztec 3, but the language itself we're constantly iterating on in looking for that goal. So right now it's mainly the contract syntax. And how is it better compared to other ZK languages? Well, one of our main things that we try to kind of give you guys from this talk is that classic Noir, vanilla Noir on its own, is much safer to use for maybe not pro ZK cryptographer dev. We wire the constraints for you, and assuming there's no bug in the compiler, you don't have to fear bugs like you saw in Tornado Cache, because the Noir compiler will write it for you. We also are, at the same time, while being very secure, try to be very syntactically pleasing, and we try and mimic Rust a lot with our syntax.
Something coming as well, isn't there? Generics?
Generics already exist.
There we go.
We have like numeric generics. Maybe like there's things that are kind of in the roadmap as well, like full compile time expressions, and maybe like vectors is one of the bigger features as well. That's kind of been in the roadmap for a while, but we've been working a lot on getting unconstrained functions contract syntax in recently. But the classic language features are also all still at top of mind.
So there's a set of packages called Noir Wasm. Recently they've just been updated. I'm actually working on a showcase application. All of you guys I met at Denver, I know some of you guys are in here, have seen me talk about it. I have a CTF that I was meant to release during Denver but didn't, and I still haven't released because we've been super busy. But it's upcoming, and I'll release all boilerplate around that as well. I'm pretty sure, let me get some links for you. There are some great boilerplate examples that have been created by our DevRel team that allow you to prove things inside the browser. There's also, I think there's a white noise template called nplate, which has got some really good TypeScript bindings set up that you can really easily create proofs in. But I would be very careful with the versioning that you're using whenever you download TypeScript packages, because you can see here that the target directory creates a proof.pk and a proof.json. Previous versions have different outputs, so they might not work with the current TypeScript version you're using. Maxim's just posted Awesome Noir, which has got a lot of the good resources inside of it. I think it's got the boilerplates in it as well, which is good. So that's definitely something that's on the roadmap, or just general recursion in general. But as Max was saying, we've been doing a lot of Aztec 3 work recently that's taken the brunt of our time. That's going to be coming, and I know that's going to be a killer app once it does exist, because if you could write in any other library, like even if you could just write Halo 2 proofs, or take like some kind of Halo 2 ML library and then actually verify it on chain, it would be incredible. I feel like that's been at the top of the list for a long time, but it's just not that easy. But we are working on it. It's getting there.
Yeah, we would like recursion in general, and like in the spirit of Noir, also being like backend agnostic. Like Noir could be, proven in Grot 16. We want to still be able to verify that in a Noir circuit as well. So, recursion in general is a big thing that we want to add, but other priorities have gotten in the way.
Technically, you can have an unlimited amount. There's like Noir compiles to something called a Seer, which you can then glue to any backend. So you can kind of write a bridge between a Seer and a certain proving system that will lay down constraints. How many programming languages are part of it? Like Rust?
It's written in Rust, and it's also like Rust-like as well. That's in the syntax, but I'm not entirely sure what you mean by your question. How many programming languages? Thank you, everybody.